Alright, so we are going to solve two Chapter 3 homework problems, and we are going to start with 3.2. So this question says, liquid mixtures of sodium and potassium are used in some nuclear reactors as coolants that can survive the intense radiation inside reactor cores. Calculate the energy required as heat to melt 250 kilograms of sodium metal at 371 kelvins. So this problem gives us the mass of our metal and the temperature. So from that, to calculate the heat, the equation we're going to use is Q equals N, the number of moles, times the standard enthalpy of fusion of our sodium metal. So our standard enthalpy of fusion of our sodium metal is 2.60 kilojoules per mole. And this value is not in the back of the book, so you have to look it up. And so I found this value on chempaths.cheddl.org, and this is at the melting point of sodium, which is 371 kelvins, which was in our book. So moving on, next we're going to find the number of moles. So we had 250 kilograms of sodium, and so first you convert kilograms to grams, and then using the molar mass of sodium, 22.99 grams, we can find the moles, which gives you 1.09 times 10 to the fourth moles. So now we have everything we need to solve the problem, and so we plug everything in. So Q equals 1.09 times 10 to the fourth moles times 2.60 kilojoules per mole, and our answer is 2.83 times 10 to the fourth kilojoules. So that is how we solved that problem. And now we're going to move on to chapter 3, number 22, which is right there. So this problem reads, the complete combustion of fumaric acid in a bomb calorimeter released 1333 kilojoules per mole of fumaric acid at 298 kelvins. So first we're going to calculate the internal energy of combustion. So since we're taking place in a bomb calorimeter, we're going to assume that there is constant volume. And because there's constant volume, our standard internal energy of combustion equals our heat at constant volume. Therefore, our standard internal energy of combustion is negative 1333 kilojoules per mole, which is what the problem gave us. Now in part B, we need to calculate the enthalpy of combustion. So here's the equation for the problem that we are using. So you have fumaric acid and oxygen, and so combustion then gives you carbon dioxide and water. So the equation we need for this problem is the standard enthalpy of combustion equals the standard internal energy of combustion plus delta nu times RT. So first we're going to find the delta nu of gas. And so if you look, we have 4 moles of carbon dioxide as the product and 3 moles of oxygen as a reactant. So we're simply going to use 4 minus 3, which equals 1. So we've taken care of that value. Next, we're going to go to R. And since our internal energy is in kilojoules, we're going to convert R into kilojoules. So you simply do that by dividing by 1,000. And now we have 0.008314 kilojoules per mole. Now, next, so as we just found in part A, our standard internal energy of combustion is negative 1333 kilojoules per mole. And finally, the problem tells us that our temperature is 298 kelvins. So, again, here's our equation, and we're going to plug everything in. So our standard enthalpy of combustion equals negative 1333 kilojoules per mole plus 1 times 0.008314 kilojoules divided by Kelvin per mole and times 298 kelvins, giving us an answer of negative 1331 kilojoules per mole. Finally, we're going to find the enthalpy of formation of lactic acid. So this is the equation we need, and the standard enthalpy of formation of lactic acid equals it'll be the products minus the reactants. So we have the standard enthalpy of formation of carbon dioxide times 4 plus the standard enthalpy of formation of water times 2, the coefficient, minus our standard enthalpy of combustion of fumaric acid, which we just found in part B, which is negative 1331. So we're going to plug everything in to get 4 times negative 393.51 kilojoules per mole plus 2 times negative 285.83 kilojoules per mole minus negative 1331 kilojoules per mole. So as I just previously stated, our negative 1331 comes from part B, and then our negative 393.51 and negative 285.83 are values that I took from the back of the book. And so you just look them up under the standard enthalpy of formation of carbon dioxide and water. So by plugging all of that in, we get our final answer that the standard enthalpy of formation of lactic acid is negative 815 kilojoules per mole.